In 1943, a warship vanished before the eyes of witnesses and then reappeared in another place in another time. Was this part of a secret experiment? Or was it proof that time travel is possible? Have you ever dreamed of going back in time to change a moment, or of moving forward to discover what the future holds? Time travel has been a dream, a fantasy, and science fiction has explored it for decades. From The Time Machine by H.G. Wells, through Star Trek, to Christopher Nolan's Interstellar, which is not the same as Star Trek, cinema has fueled our imagination with worlds where time can be bent and jumped across. But what does science really say about time travel? Is it mere fantasy, or is there a real basis to believe that someday we may cross this threshold? Today, we are going to explore theories, discoveries, and the boundaries that physics imposes on us. And you may be surprised by how close some ideas really are. Prepare yourself for an astonishing journey where space and time intertwine in ways that defy our reality. This is Time Travel, explained by science. This is Infinite Curiosity, where the impossible becomes a question. What if everything you knew was just the beginning? Imagine that the universe is not static, but rather a vast elastic network that can twist, curve, and compress. In 1935, two great physicists, Albert Einstein and Nathan Rosen, introduced a revolutionary idea in physics: wormholes. Also called Einstein-Rosen bridges, these would act like invisible tunnels connecting two distant points in space-time. But what if these tunnels did more than just link places? What if they could also connect different points in time? According to theory, if one end of a wormhole is moved at speeds near light and then brought back, the two ends could end up at different times. That would mean that entering one end could land you in the past or the future. However, there is a major obstacle. Physics predicts that these tunnels would collapse almost immediately, making travel impossible. To keep them open, we would need something extremely unusual: exotic matter. This hypothetical substance would have extraordinary properties, such as negative pressure or negative energy, capable of holding these tunnels open like an invisible scaffold. Does exotic matter exist? So far, only in theory. But certain quantum phenomena, like the Casimir effect, a force measured between two very closely spaced metal plates, might be a hint that it is not purely imaginary. In Interstellar, physicist Kip Thorne, Nobel Prize winner and scientific advisor for the film, helped portray these concepts in a realistic manner. In the story, an advanced civilization places a wormhole near Saturn to enable interstellar and possibly temporal travel. Could something like that be possible? Science has not yet found direct evidence of wormholes in the universe, but the equations do allow them. Some scientists believe they may exist on microscopic scales, within a quantum foam, the chaotic, fluctuating fabric of space, time at the subatomic level. Others speculate that with advanced technology and manipulation of negative energy, a quantum wormhole could be enlarged to become traversable. But for now, all this remains speculation. What is holding science back? The lack of observational evidence, technological limitations, and the enormous energy required to sustain them. Einstein's general relativity opens the door, but quantum mechanics still does not fit entirely into the puzzle. Could the Large Hadron Collider at CERN, the world's largest physics laboratory in Switzerland, help us understand these mysteries? This collider studies the most fundamental particles, recreating conditions just after the Big Bang. If one day we manage to understand the relationship between gravity, time, and quantum particles, we could not only confirm the existence of wormholes, but learn how to cross them. What if they already exist, waiting to be activated by a sufficiently advanced civilization? Could they be the key to opening the doors of time itself? Fascinated by the universe's greatest mysteries? Subscribe, comment, and join us as we explore them with the most advanced artificial intelligence. What if we did not need to go through a tunnel to travel through time? What if, instead of crossing a wormhole, we could bend the universe around us? That is the essence of the warp drive, one of the most audacious and revolutionary ideas in modern theoretical physics. In 1994, Mexican physicist Miguel Alcubierre proposed a mathematical solution to Einstein's equations that would allow faster-than-light travel without breaking any physical laws. How would this work? The key is not moving the ship through space, but moving space around the ship. Imagine space, time as a carpet. Instead of walking on it, you roll it behind you and unroll it in front of you. Your position stays the same, but space moves. This is how the warp drive would function. A bubble of deformed space that would allow an object to move at superluminal speed without violating the rules of the universe. But what does this have to do with time travel? According to relativity, space and time are intertwined. If we can deform space, we also alter time. A warp drive could therefore open the door not only to interstellar travel, but to temporal jumps. There is, however, a tremendous challenge: the energy needed to create and sustain such a bubble. Alcubierre's original calculations suggested that more energy than the entire observable universe would be required, something impossible with current technology. But science does not stop. In recent years, physicists like Harold White have proposed modifications to the model that could drastically reduce the energy needed. They have even built small experiments at NASA to explore these concepts. Like wormholes, a warp drive would require exotic matter with negative energy to serve as the fuel of space-time. Despite these challenges, this theory remains one of the most promising for interstellar and possibly temporal travel. In popular culture, warp drive was popularized by Star Trek, which showed us a future where the Enterprise travels at impossible speeds, spanning galaxies and possibly time. Could Star Trek be a prophecy? Are we truly approaching a future where the speed of light stops being a limit and becomes just the starting point? Maybe, in a future not too far away, these warp bubbles will allow us to leap centuries or millennia into the future. But if we can move forward, could we also go backward? Is speed the key, or perhaps direction? Warp drive invites us to imagine a universe where bending space is the gateway to new worlds and new times. Would you be ready to cross that threshold? Time travel sounds fascinating, but it is not all smooth or risk-free. Every time we think about manipulating time, temporal paradoxes arise, logical traps that can break the coherence of the universe. Imagine going into the past and changing a single detail. You prevent an accident, save someone, or make a different decision. What would happen to the present? Would your original timeline be erased? Or would an alternate reality emerge? One of the most famous paradoxes is the grandfather paradox. Suppose you travel back and prevent your grandparents from meeting. How could you have been born to travel back and make that change? These contradictions are a puzzle for both physics and philosophy. Some theorists believe time is like a river. Any change in the past alters the entire flow, erasing the original timeline and creating a new one. Others propose the theory of parallel universes or multiple timelines, where every change spawns a coexisting reality alongside the original. Time travel would then not be a matter of moving back or forward, but of jumping to a new reality, avoiding paradoxes. But even if paradoxes are resolved in theory, altering the past raises deep ethical and existential questions. Do we have the right to change what already happened? Who decides what changes are good or bad? In physics, some models propose that the laws of the universe might protect temporal coherence. This is known as Novikov's self-consistency principle. Any action taken by a time traveler would already be part of the known past, making paradoxes impossible. But what if reality is more flexible? If time is a malleable fabric we can deform with unpredictable consequences? Temporal paradoxes remind us that, beyond the fascination of time travel, we face a profound mystery where logic, physics, and ethics intertwine. Would you risk everything for a single temporal jump? Or is the cost of changing the past too high? Time, like a labyrinth, invites us to explore its secrets with caution. Once we cross that line, nothing can remain the same. While we dream of traveling backward or forward, our daily experience of time seems to have only one direction. It always moves forward, never backward. This is known as the arrow of time. But why does time only flow forward? What prevents it from reversing? To understand, we must turn to thermodynamics, the branch of physics that studies energy and heat. One of its most fundamental laws, the second law of thermodynamics, tells us that entropy, a measure of disorder, always increases in an isolated system. Imagine a hot cup of coffee on a cold table. Over time, the coffee cools, heat disperses, and the system becomes more disordered. This process is irreversible. You will never see a hot cup form spontaneously from cold liquid. Thus, the arrow of time is tied to this inevitable increase in disorder. Time moves forward because the universe marches toward a state of greater entropy. There is more. Time is also connected to the expansion of the universe. Since the Big Bang, our cosmos has expanded, marking a before and after. Some physicists suggest that this expansion also imposes directionality on time, a sense of moving forward toward a colder, more diffused future. So, even though the equations of physics, like Newton's laws or relativity, are time-symmetric, time's arrow emerges from statistics, chaos, and the evolution of the cosmos. But what if we could reverse the arrow? Could time flow backward under extreme conditions? Some quantum experiments and black hole theories explore these possibilities, but answers remain unclear. For now, the arrow of time reminds us that, while we may dream of traveling to the past, reality may be built to prevent it, preserving the natural order of the universe. It is as if time is a current that carries us forward, with no turns allowed. And so, with every passing moment, we become part of this unstoppable flow, moving toward the unknown. One of the greatest theoretical obstacles to time travel is the famous temporal paradoxes. The best known is the grandfather paradox. Imagine that you could travel to the past and accidentally, or intentionally, prevent your grandfather from meeting your grandmother. That would mean one of your parents would never have been born, and neither would you. How then could you have traveled back in time in the first place? This contradiction is at the heart of the paradox. Physicists and philosophers have pondered this for decades, looking for answers in everything from classical physics to quantum mechanics. One possible solution is the theory of multiple timelines or parallel universes. According to this idea, by changing something in the past, you create a new timeline, a separate universe, where that event plays out differently. In that new universe, perhaps your grandfather never meets your grandmother and you are never born. But in your original timeline, everything remains intact. That way, the logic and causality are preserved. Another theory, proposed by physicists like Novikov, is the self-consistency principle. which asserts that any action you take in the past was already part of history and thus cannot change it. For example, even if you travel to the past, you would not be able to stop your grandparents from meeting because, in some way, your actions were always meant to allow it. This principle would prevent paradoxes and keep temporal coherence intact, although it would limit free will in the past. But what does modern physics say about these ideas? Quantum mechanics, with its probabilistic nature and strange rules, opens up multiple possibilities, although it is still far from providing definitive answers. Experiments with subatomic particles that appear to exist in multiple states at once suggest that reality may be more complex than we imagine. For now, temporal paradoxes are more than philosophical puzzles. They are barriers that science must overcome if it ever hopes to unlock the door to the past. One of the greatest questions about time is why we experience it as a single direction, always pointing forward. In physics, this concept is known as the arrow of time, and it is closely tied to entropy, a measure of disorder in a closed system, as described by the second law of thermodynamics. That law tells us that the universe's entropy always increases, meaning disorder grows with time. This explains why past and future are not the same. The past had less entropy. The future is ever more disordered. It is this irreversibility that lets us remember the past but not the future, and ensures that causes always precede effects. However, fundamental laws of physics, like Newtonian mechanics or relativity, are time-symmetric and do not favor one direction. That has led scientists to investigate how time's arrow emerges from these laws and the universe's statistical behavior. Some theorists suggest that the Big Bang marked the starting point of this arrow of time, establishing a low-entropy initial state from which everything evolved. But what if we could locally reverse entropy? Would it be possible to travel back in time? So far, entropy seems inexorably tied to increasing, creating a natural limit on any backward time travel. Time's arrow is one of the reasons why, although mathematics may allow temporal journeys, reality may have rules to prevent them. Thus, time becomes not only a dimension for measuring events, but also an experience deeply linked to the universe's evolution. Fascinated by the universe's greatest mysteries? Subscribe, comment, and join us as we explore them with the most advanced artificial intelligence. Imagine going back in time and changing a tiny detail, such as stepping on a different leaf or missing a random encounter. Do you think that could alter your entire future? This is the essence of the famous butterfly effect, a concept popularized by chaos theory, which holds that small actions can have huge, unpredictable consequences. In the context of time travel, this effect generates paradoxes and unsettling questions. For example, what if by going to the past you prevent one of your grandparents from being born? This is the grandfather paradox revisited. If you prevent your ancestor from existing, then you could not have been born to make the trip back. How is this conflict resolved? There are several theories. A popular hypothesis is the multiverse. Every change in the past creates an alternative timeline, a parallel universe where events unfold differently. This would prevent paradoxes but also mean that the traveler never changes their own timeline. They only jump to another reality. Another possibility is that time is self-consistent. Any attempt to change the past simply ends up causing the same outcome, forming a closed loop which protects itself. Some scientists believe paradoxes signal that backward time travel might be impossible, or that nature has built-in mechanisms to avoid it. But the fascination continues, and science fiction explores these paradoxes relentlessly, challenging our understanding of time and causality. Ultimately, The butterfly effect and temporal paradoxes remind us that time is a fragile fabric, and tampering with its threads may have unimaginable repercussions. Even though many physical equations allow time to move forward or backward, in our everyday experience time only moves forward. This phenomenon is known as the arrow of time, and it is deeply connected to the second law of thermodynamics, which states that entropy, the disorder of a closed system, always increases. Imagine a hot cup of coffee spilling on a table. You will never see it flow back on its own into the cup. That increase in disorder sets a clear direction in time, from order to chaos. The arrow of time is one reason why backward time travel seems impossible. Reversing entropy would violate known physical laws. There's more. Cosmology shows that the universe itself has an arrow of time, from the Big Bang to its possible future. Some physicists speculate that if the universe ever contracts instead of expands, time's arrow might reverse, causing time to flow backward. These ideas challenge our intuition and open the door to fascinating theories about time's nature and reality. Additionally, quantum mechanics suggests that at the subatomic level time may behave non-linearly, although we still do not fully understand how that impacts macroscopic reality. In summary, the arrow of time is an invisible compass guiding our past, present, and future, and it shows us why backward time travel remains an uncharted frontier full of mysteries. One of the greatest theoretical challenges for time travel are temporal paradoxes, dilemmas that question the logic of the universe itself. Imagine traveling to the past and accidentally preventing your grandparents from meeting. What would happen to your existence? This is the famous grandfather paradox. If you were never born, how could you have traveled back to prevent your birth? These contradictions suggest that time travel could break the basic rules of cause and effect, creating loops that are impossible to resolve. Some scientists propose fascinating solutions. The parallel universes theory suggests that by changing the past you simply create a separate reality, disconnected from the original. Thus, even if you alter past events in another reality, your original timeline remains untouched. Another idea is Novikov's self-consistency principle, which states that the universe ensures that you cannot alter events that already happened, preserving temporal coherence. In this model, the universe makes sure that any action taken in the past was already part of history, preventing paradoxes. But these theories remain speculative and lack experimental evidence. The truth is that temporal paradoxes show us that time travel is not just a technological challenge. It is a challenge to the very structure of reality. From Einstein's equations to tales of popular culture, time travel remains one of humanity's greatest mysteries. We have explored how wormholes and warp drive invite us to imagine the impossible, and how quantum physics challenges our perception of time. We have also seen paradoxes, ethical dilemmas, and anecdotal stories that, even without being conclusive, keep our curiosity and sense of wonder alive. Perhaps we will never build a time machine in our lifetime, or perhaps we are one discovery away from taking a leap we cannot yet conceive. For now, the true journey could be learning to value the time we have, understanding that each second is a unique opportunity. The mystery of time remains open, and even if we cannot cross its boundaries yet, we continue to explore, dream, and search for answers. And you? What would you do if you could travel through time? What moments would you live or change? Time is the greatest gift we possess. Let us make the most of it. If this topic fascinated you as much as it fascinated me, do not forget to subscribe to the channel, like the video, and activate the notification bell so you will not miss future episodes. Here, on Infinite Curiosity, We continue to explore the most incredible mysteries of the universe, and you are part of this adventure. Now I want to know from you, if you could travel through time, which era would you visit? What would you change or what would you like to discover? Leave your answer in the comments. I would love to read your ideas and dreams. Thank you for joining me on this temporal journey. We will see each other in the next adventure.